Dating as far back as the 16th century, NIM is a strategy game which involves multiple piles of discrete objects, with two players taking turns at removing one or more objects from a single pile. Two variants of the game exist: normal play, in which the player to take the last object wins, and misère, in which the player to take the last object loses. NIM is a thoroughly documented game of pure math, with a complete theory developed in the early 20th century. Provided a player knows the winning strategy and the board is in a winning state, it is impossible for them to lose the game. Through the course of this presentation, we will discuss the challenges involved in finding a solution to the game, detail the winning strategy on a conceptual level for both normal and misère play, as well as demonstrate and discuss our specific software implementation of the strategy and its limitations. Finally, we will conclude the presentation with a brief discussion on the unit learning outcomes and an overview of contributions made by each member. In NIM, the immediate challenge lies in the potentially large number of possible moves and paths the game can take. Consider a game with 3 piles consisting of 3, 4, and 5 objects. The player can opt to remove from 1 to n objects from any one pile, giving 3 plus 4 plus 5, 12 possible moves. From every branch, the player's opponent then has 12 minus k possible moves, where k is the number of objects removed by the first player. As you can see, the size of the state space can rapidly grow out of control and will be near impossible for humans to calculate while playing. To combat this, a strategy needs to be developed which enables a player to find the best possible move based on the current board state, without having to calculate every possible endgame. The strategy also needs to be adaptable to the misère variation, which will reverse the win condition. As you will see, the winning strategy is not one that is immediately obvious and requires exploration of binary numbers. I'll hand over to Sarah now to present an overview of the winning strategy.
Thanks, Ian. In 1901, Charles Booton, an American mathematician, developed a complete mathematical theory of NIM and determined a winning strategy for a player. The strategy lay with binary, representing the number of objects in a pile by their binary notations and then performing a specific operation on them called NIM sum. Let's walk through this idea with an example game. Here we have 4 piles of objects. Each pile is represented by a different colour. The blue pile has 1 object, the red has 3, and so on. And these values, which are written beside each pile, are part of the decimal number system. Whereas each digit of the decimal system represents an increasing power of 10, binary represents increasing powers of 2. Looking at our game, we can easily write down the number of objects in each pile in binary notation by finding the biggest power of 2 that goes into the number. Looking at our purple pile, we can see that 2 to the power of 2 is the biggest power of 2 that goes into 7. With 3 objects left, the largest power of 2 that goes in 3 is 2 to the power of 1, leaving us with 2 to the power of 0 objects left. So we can write this down as 1, 1, 1. And similarly, we can do so with the 3 other piles. Looking again at our game, its state is what we call balanced. At each column, and remember, each column represents a power of 2, there are an even number of objects. Now let's say a player removes 1 object from the purple row. There are now an odd number of objects in the 2 to the power of 0 column, and the game state is now unbalanced. If just one of the columns has an odd number of objects, the state is unbalanced. Interestingly, this pattern of changing from a balanced to an unbalanced state is inevitable. No matter how many objects we remove from any one pile in a balanced state, the game state will become unbalanced. Contrary to this, from an unbalanced state, you can change to a balanced state or remain at an unbalanced state, depending on your move. Looking at our example, we could remove the 1 blue object and the game becomes balanced, or we can keep the game state unbalanced by removing 2 purple objects. Calculating the balance of the game is done by a calculation called the NIM sum, named for this game, but it's actually just the common exclusive OR operation. This operation can be thought of as there being 2 objects and being able to have one or the other, but not both. Due to its commutative and associative properties, this operation generalizes to more than 2 objects in a way that partitions even numbers of objects from odd numbers. Now let's use our example again to understand this. We can take our game state as before and write down the column values in their binary digits. Looking at the first column of the balanced state, we can see that 2 rows have 2 to the power of 2, and since we can have one or the other but not both, exclusive OR tells us to write a 0 for that column sum, because we can't have both. Both the second and third column also have an even number of 1s, and therefore we can write down 0 for these two. Our NIM sum is this exclusive OR sum written at the bottom, 0, 0, 0. This value of 0 tells us that our game state is balanced, and this generalizes to every balanced state. The NIM sum is always 0. Contrary to this, our unbalanced state has 0, 1, 1 as the nim sum, due to the 2 to the power of 0 and 2 to the power of 1 columns having uneven total values. Any nim sum that is not equal to 0 is an unbalanced state. The ability or inevitability to change states is the key to nim which Charles Booton unlocked. The winning strategy is to finish every move with a balanced state, which, as we've just learned, is always possible if the game is unbalanced before your move. So, the game outcome depends on two things: who plays first, and what is the beginning state of the game. If a game's opening state is balanced, the first player will inevitably lose if their opponent plays perfectly. That is, if the opponent leaves the game balanced after every turn. The opponent's win is inevitable because when there are no objects left, the game is balanced, and in the normal game of nim, the player who removes the last object wins. Now let's have a look at this written out in pseudocode for each move. First, we calculate the nim sum. If the nim sum is greater than 0, the game state is unbalanced, and the player can make a move that balances the game. By decreasing the quantity of one pile of objects to the amount equal to the exclusive OR operation applied to the pile size and the nim sum of all piles, the player is guaranteed to balance the game. If the nim sum is equal to 0, the game state is balanced, and it doesn't matter what move is made, as the result is an unbalanced state. And therefore the player chooses a random pile to remove a random number of objects from. And now here's Riley to talk about the implementation.
Cheers! For the implementation, I'm going to be talking about the main loop, and then I'm going to be talking about individual functions in the Python program. So for the main loop of this function continues until we set the value gameover to be true. Firstly, we call print board to display the current state to the terminal. Then, we check the computer move variable to determine which player's turn it is and call the appropriate function to get their move. We then call check win to determine if either player has won, and if so, set game over to true to end the program. Finally, we say computer move equals not computer move to change which player's turn it is, and then we go back to the start of the loop. So the check empty function. The check empty function uses a for loop to cycle through elements in a list. If any of them are not 0, then we return false. Otherwise, we return true. To check if we're in a winning state, we use the check win function. This function calls the check empty function to see if the board is empty. If it isn't, then we return false. If it is, then someone has won. After checking whether the game is a Messier game and whose turn it is, we return the appropriate result. In the getComputerMove function, we check if Messier mode is set. If so, and there are one or less piles with more than one disk, then we check to see how many piles are left and what the size of the largest pile is. If there is an even number of piles left, or if the largest pile is of size 1, then we empty the largest pile. Otherwise, we reduce the largest pile to size 1. Outside of the special Messier endgame case, we apply the standard strategy, which is to try to find a move that makes a nim sum 0. To do this, we use XOR to get the nim sum of the group nim sum and number of disks in each pile. If this value is less than the value of the pile, then we consider changing the number of disks on this pile to the nim sum that we just calculated. If the new nim sum is 0, then this is a valid move, and we make it. If after these checks we can't find any valid moves, we remove a random number of disks from a random pile. In the getUserMove function, we ask the user two questions: which pile they want to take disks from, and how many disks they want to take. To ask a question, we use a while loop to ask the question until we get a valid answer. To convert the function to an integer, we use the built-in int function, combined with a try-except structure to deal with errors in conversion. We then make sure that the number is valid, such as by checking to make sure that it's greater than 0. Once we have the user's answers, we remove the disks from the pile's representation in the list and print a message detailing what's been done. So for the group nimSum function, we use a for loop to successively XOR all elements of the list against each other and then return the result. In the print board function, we use an enumerate construct on the list of piles, and then we print each pile along with the number of disks in that pile. We then print a new line. Now, the first function that we call at the very start of the script is called initialize piles. This function creates the initial game board. It chooses a random number of piles between 2 and 5, which we'll call n, and assign one token to each pile. To store the number of tokens in each pile, we use a list of integers. With the remaining n plus 1 tokens, we use a for loop to distribute them randomly among piles. And now Denika's going to detail the limitations and constraints of our solution.
Thanks, Riley. There are a few limitations to our model. The first would be the fact that it is only designed for 2 players, a computer and a human. If there were more players introduced to the game, as is the case with some of the many different variations of the game of NIM, the strategy and algorithm would have to be modified to accommodate this. The next limitation of our model of the game is the fact that the computer will always win unless the human plays optimally throughout the entire game. And in order for the human to play optimally, they need to be able to do binary addition. This would be considered a limitation because there would be not many people who could play a perfect game each round, thus would make the game not very fun or evenly matched, and it wouldn't be played very often. The final limitation would be that if both the computer and human players manage to play a perfect game, the winner will always be the person who begins the game, as this means they are already in the position since the beginning to deliver the final and winning move. The unit learning outcomes have been demonstrated throughout this submission as follows. ULO 1, through the use of binary addition to develop a model that solves the game of NIM. ULO 2, through the design and implementation of the Python Game of NIM program created by our team members Riley and Ian that we used to demonstrate the effectiveness of the algorithm and proposed solution. And finally, ULO 3 has been demonstrated throughout this presentation as we explained the theory behind the challenge, discussed the algorithm chosen to be implemented, and provided an overview of the design and use of our program. To conclude this presentation, we have prepared a table that demonstrates the different tasks undertaken by our team. As you can see, each team member attended group meetings, conducted independent research, contributed to discussions, and prepared documentation, as well as contributing to the presentation by recording the sections of the script that they wrote. Additionally, Danica set up the communication media of Slack, Trello, and OneDrive, and prepared the slides for the presentation, while Sarah polished the presentation and integrated the voice recordings made by each member. Finally, Ian and Riley worked together to create the Python program.